You know, we're surrounded by AI that can learn all sorts of incredible things. But can it actually understand anything? That's the big question we're tackling today. We're going to look at how we can teach AI to go beyond just figuring out what works and to finally start asking that one fundamentally human question. Why?
So let's just start right there. I mean, what is the real difference between learning and understanding? Think about it like this. You can learn a recipe, right? Memorize every single step, follow it perfectly, and bake a loaf of bread. But do you understand the chemistry that's actually making that dough rise? That difference? That gap? Well, that's at the very heart of the next giant leap for artificial intelligence.
And to get there, to bridge that gap, we've got to first look at how a lot of today's most powerful AIs actually learn. Because in essence, they're basically just incredibly sophisticated trial and error machines.
So a super popular method for this is called reinforcement learning, or RL for short. The best way to think about it is like you're training an AI to play a video game. You drop it into some environment, it looks around, and it takes an action. If that action gets it closer to the goal, like finding a treasure, boom, it gets a reward, a point. Do that millions and millions of times, and eventually it builds up a strategy, a sort of rule book for getting the highest score possible. It's an absolutely amazing way to learn what to do. But, and this is the crucial part, that AI is just learning associations. It's figuring out that doing X when it sees Y usually leads to a reward. It never ever learns why. It totally masters the what, but the why is a complete black box. And honestly, that's a hard ceiling on its intelligence. It's a ceiling that could be downright dangerous in really complex situations, like, say, an autonomous car, or an AI making a medical diagnosis.
So, the big question is, how do we break through that ceiling? Well, to help us frame this whole problem, we're going to borrow a brilliant idea from the Turing Award-winning computer scientist Judea Pearl. He calls it the ladder of causation.
Okay, so this ladder has 3 rungs. The very bottom rung is association, or just seeing. This is all about spotting patterns in data. Asking, if I see X, what are the chances that Y will happen? The second rung is intervention, or doing, and this is where that traditional reinforcement learning we just talked about hangs out. It's about actively trying stuff and asking, okay, if I do X, what happens to Y? But the top rung, man, this is where the real magic happens. It's called counterfactuals, or imagining. This is where you can ask, what would have happened to Y if I had done something different?
And look, don't just take my word for it. Judea Pearl himself basically said that without a causal model, a map of how the world works, an AI is just stuck. It can see patterns, it can even act on them, but it can't reason about the world in a deeper way. It simply can't climb that ladder to get to true understanding.
So let's really dig into that top rung of the ladder, because this is the power of what if. It's where simple learning really transforms into something much, much deeper.
So just imagine this for a second. What if an AI agent could do more than just act? What if it could look back at an outcome and think to itself, okay, I gave the patient treatment A and they got better. But what would have happened if I had given them treatment C instead? That ability to explore these alternate past realities, well, that's counterfactual reasoning.
And let me be clear, this isn't just a small improvement. This is the giant leap from just seeing that two things happen together, that's correlation, to actually knowing that one thing causes the other to happen. It's the leap from learning to real, genuine understanding.
So, how in the world do we build an AI that can actually make that leap? Well, it happens when you bring together 2 incredibly powerful, but usually separate fields of study.
And here it is. This is the big breakthrough. It's the marriage of causal inference and reinforcement learning. When you put them together, you get causal reinforcement learning, or CRL. And by combining them, we can finally build an agent that's able to climb all the way to the top of that ladder.
So here's how this actually works under the hood. A causal RL agent isn't just looking at a sea of raw data anymore. Instead, it's filtering all of that information through what we call a causal model. You can think of it like a mental map, or a blueprint of how the AI believes the world actually works, a diagram of cause and effect. And it's this model that lets it run all those what-if scenarios in its head, leading to way smarter, more reasoned decisions.
Okay, I know what you're thinking. This all sounds really cool in theory, but does it actually make a difference in practice? Well, let's take a look at the data and see what happens when you give an AI this power of causal reasoning.
So what you're looking at here is the proof, plain and simple. We're comparing a few different AI agents. The red and blue lines, those are your traditional trial and error RL agents. But that green line, that's our new causal agent. On the left, you've got performance. Higher is better. On the right, you have something called cumulative regret. The easiest way to think about regret is as a score for mistakes.
Every time the agent fails to make the absolute best choice, its regret goes up. So for that chart, lower is better. And I mean, the results are just wow. They're crystal clear. On the performance chart, the green line just shoots to the top and stays there. It learns the best strategy way faster. Then look at the regret chart. The red and blue lines just keep climbing. They keep making mistakes. But our green causal agent, it flatlines. It basically stops making mistakes way sooner than the others because it understands why. It doesn't need nearly as much clumsy trial and error. It just learns better, faster, and smarter.
So we'll leave you with this thought. We are right on the verge of creating AIs that don't just learn, they actually understand. They can reason about cause and effect. They can imagine what might have been. So the question we have to ask ourselves is no longer just, what can AI do? But as it keeps climbing this ladder of understanding, what truly complex, high-stakes decisions in medicine, in science, in policy are we going to be ready to trust it with next?